Hello everyone, welcome back. We'll continue on the reaction of alcohols, which is dehydration of alcohols. We have already seen that the alcohol group, that means the OH group, cannot just live by itself for dehydration. It has to be activated or protonated by a strong acid, such as sulfuric acid, tosic acid. We have seen this in our previous lecture. Now, what we're going to do is just use another combination of reagent, phosphorus oxychloride and pyridine, to effect the same reaction, that means the dehydration of alcohol into alkenes. The main advantage of this reaction is this reaction goes through an E2 mechanism. That means the abstraction of beta hydrogen and the leaving group, which is the OH, or activated OH, would happen simultaneously. In the previous videos, I have already shown you the dehydration of alcohols mainly goes through a carbocation intermediate. Hence, the carbocation intermediate is prone to rearrangement. It shifts to stabilize the secondary carbocation into a tertiary hence it leads to shifts where the double bond would be formed. But in this particular phosphorus oxychloride and pyridine combination, so this is a combination of phosphorus oxychloride and pyridine, in the reaction would give you dehydration product, which is the same elimination of water, but through an E2 mechanism. So the main emphasis would be it is an E2 mechanism. So this is a reagent combination, phosphorus oxychloride and pyridine. So if you see this combination in a reaction, it's a dehydration of alcohol to give a cyclohexene or an alkene. And importantly, you should also remember that it is an E2 mechanism, so you don't form carbocation in the mechanism. That's the main distinction. So I will show you briefly what the mechanism looks like. As you know, the hydroxide has to be activated. The activation is because the OH group has a lone pair of electrons. That makes it basic, or it's a good nucleophile, or it's reached out to be a nucleophilic center. It attacks a positive center. Phosphorus, being surrounded by 3 chlorines around it and oxygen, all the electron is moved away from phosphorus. So the phosphorus center is very positive. That means it's prone to be attacked by the OH, lone pair electrons on oxygen, to be attacking the phosphorus, because phosphorus has a relatively some sigma positive charge on it because of electron withdrawing group on the central atom phosphorus. So the arrow is that it attacks this, then the chloride, one of the chloride, of course, should leave. Then it gives you an activated system which looks like this. So the initial step is the activation of the oxygen, the hydroxide. Since electrons are donated to phosphorus, now you have a plus, and you would have phosphorus still like this, Cl, Cl. One of the phosphorus would leave as Cl minus around. Now you have this group, which is very activated group now, but since you have a pyridine floating around, that is a base, this is a very acidic proton now. So it would neutralize that proton by picking it up. So pyridine, which is this molecule, a very base, an organic base, because of this lone pair of electrons, the hydrogen would be abstracted by the pyridine. Then this pair of electrons would neutralize that positive charge, and you would produce a neutral activated system. That means O, P, O, Cl, Cl. So you will have that. So that is now, it's already a good living group now. You have formed a good living group at this point. This is now a good living group. That is the whole purpose of reacting it with phosphorus oxychloride. Now you have a good living group, and now you have beta hydrogens here. So one of the beta hydrogens would be just picked up by a pyridine. Pyridine is in excess amount. That's the base you have. So sorry, I forgot here to put phosphorus oxychloride and pyridine. So now pyridine comes in, it's a base in the reaction. It would pull off one of the acidic protons, and this pair of electrons would make the double bond. Now this, as supposed to do, it will leave. So the product, the final product, is a dehydrated cyclohexene. Water, at the end of the day, what happened is water was removed, because if you just look at here, you have one H here, one OH here. At the end of the day, the net reaction is removal of water to make a cyclohexene. Cyclohexene, double bond. Okay? This is cyclohexanol, alcohol, that is alkene. So main advantage of phosphorus trichloride, oxychloride, phosphorus oxychloride, in the presence of a base, which is called pyridine, via an E2 mechanism. This is important. This is an E2 mechanism. This is what happened. Here is the E2 mechanism. Abstraction of the beta hydrogen, formation of a pi bond, and the living group leaves. Everything happens at the same time. Hence, there is no carbocation formation, no carbocation formation in this mechanism. So that's the advantage. So you don't do rearrangement, carbocation rearrangement, or the double bond doesn't shift. So that's what you get when you react phosphorus oxychloride with, in the presence of pyridine, to dehydrate alcohols. So this is another method of dehydrating alcohols. Okay, we'll continue more with the reaction of alcohols. Okay, so now we're going to continue more on the reaction of alcohols. As you know, we already seen that the dehydration of alcohols gives a cyclohexene or an alkene in general, and we can effect that kind of transformation by reacting it with a strong acid, or also with phosphorus oxychloride in the presence of pyridine. But in this part of our discussion, we're going to discuss about substitution of the alcohol. So basically now the discussion is to substitute the OH group, for example, with halides. Because if you substitute the alcohol with halides, you can make more functional groups that can be transformed into different reactive products. So conversion of alcohol into alkyl halides is very important reaction, because alkyl halides can be transformed into different chemical products. So if you just look at this alcohol here, alcohol functional group, if you just treat it with X minus, meaning chloride minus, Br minus, or iodine minus, the reaction wouldn't go. Because what you're going to try is to kick off the OH minus. This is a poor leaving group. So this is poor leaving group. It doesn't leave easily. So you somehow need to activate also that OH to make the substitution reaction X. So what you're going to do would be the alcohol, if treated with the appropriate acid, for example, if you want to substitute this with chloride, hydrochloric acid, if you want to substitute the OH with Br minus, RBr, bromohalide, you try it with hydrobromic acid. If you want to treat it with if you want to make alkyl iodide, you could treat it with hydroiodic acid. So these three acids, for example, can be used to convert to a corresponding alkyl halide, because that would eliminate water. Water is a good leaving group. So how do you get water in this? Because you have an acid, which is H, can protonate first that, and the X minus can come and attack through SN1 or SN2 substitution mechanism. So the HX actually could dissociate into H plus and X minus. So the X minus acts as a nucleophile after the good leaving group is formed by protonation. This is an acid used to protonate the alcohol. So that's what makes a good leaving group. So in order for you to convert alcohols into alkyl halides, you need to have the alcohol converted into a good leaving group. So you could treat it with a strong acid, such as a corresponding acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. Here I want to remind you the rate of substitution or the rate of reaction is the highest with hydroiodic acid. The reason being, hydroiodic acid is the strongest acid. Hi is the strongest acid. That means it quickly protonates the OH, and I minus is also a very good nucleophile to substitute it. Nucleophile. That means if you just try to have an alkyl iodide, for example, if you have ROH treated with hydroiodic acid, you would get RI, alkyl iodide. That rate of reaction is the highest with HI, next higher would be HBr, the lowest one be hydrochloric acid. The reason being, HI is a much higher strong acid, the strongest acid among those classes. So here let's see some examples, real examples with a compound. You have here a propanol, 1,2,3 carbon alcohol. You want to convert it alkyl bromide, that means propyl bromide. What you have to do is a corresponding Br acid would be hydrobromic acid. You treat it, you can get a primary alkyl halide. So this goes by SN2 because this is a primary alcohol. So this is an SN2 reaction with a primary alcohol. How about here? You want to create this alkyl halide. That's a chloro substituted for this OH, so you use hydrochloric acid. Hence, that means this has been maybe made through SN1 because a carbocation would be formed here. The Cl minus comes and attacks that tertiary carbocation. That's how you substitute that. And here also there are also some other reagents which would include more as we discuss how to convert it to alkyl halide. Here you have zinc chloride. In the presence of hydrochloric acid, you can form the chloride, the alkyl halide. So remember, zinc chloride is a loose acid. The OH would activate it by coordinating to zinc, and the Cl minus comes and attacks this primary alcohol, primary carbon, then the chloride would be formed. Here you want to form a bromo compound. You treat it with HBr, but you get that bromo compound. Here I want to remind you something, that the activation of the using HBr to form OH2+, meaning a carbocation, would be formed here. But the Br is not right here, not on this one. You expect it to be right here, the Br. But why the Br is now here? Remember, carbocation rearrangement. So because this is protonated and the water leaves, so this is going through SN1 mechanism. SN1 involves carbocation, but the carbocation has rearranged in this case because this hydride shifted to this once the carbocation is formed. So this carbocation has rearranged by 1,2 hydride shift. Hydride shift. So the carbocation which was formed here, a hydride shifted there, forming a tertiary carbocation. From the secondary prefers the tertiary, so the Br attacks that carbon. So the attack is on this carbon. So now you have a tertiary product, a tertiary alkyl halide, not on where the hydroxide is because of hydride shift as well. So always consider, remind you again, even for elimination 1, E1 mechanism, SN1 substitution, the carbocation is prone for rearrangement. So don't forget that, because now this looks like the OH is here, but the Br is attacking, or the Br has come here, because the carbocation did not stay there. It has rearranged. The carbocation has done a carbocation rearrangement to a more stable. This is tertiary. This is secondary. So because of tertiary carbocations are more stable, the rearrangement happened by 1,2 hydride shift. This is the hydride that has shifted to this position. That's why it's now CH2. So these are kind of how you'd make alkyl halides. So this is different from elimination reaction, where you eliminate everything and form an alkene. But here, conversion of alcohol to alkyl halide is made by substitution. You substitute the OH with a corresponding, whatever you want to make, a chloride, a bromide, or iodide can be made through different reagents. You could use the corresponding acids. You could use zinc bromide or zinc chloride to substitute as chloride or bromide. So there are also other more reagents I want to introduce in this to substitute, make. Some of them actually very advantageous because they don't make the carbocation, so they make SN2 kind of substitution that gives you an not rearranged product. So we'll continue more with more reagents of converting alcohols into alkyl halides. More on conversion of alcohols into alkyl halides. These are reagents that could convert to the corresponding alkyl halide. These alkyl halides are important because these are now active to do different substitution reactions. So the alcohol can be converted easily to what you desire for. So we'll introduce two reagents here. Thionyl chloride, it is a sulfur compound, very acidic. So that's why you use it in presence of a base, pyridine. So that's a thionyl chloride. It chlorinates alcohols. That means if you have an alcohol, use thionyl chloride in the presence of pyridine, you would convert that alcohol, substitute it into the alkyl halide, the alkyl chloride specifically, because it's thionyl chloride. And the next one is relatively neutral. This is phosphorus tribromide. It converts alcohol from the alcohol into the bromoalkyl halide. So the lower portion is the phosphorus tribromide. This is a reagent, almost neutral, and very mild way to convert into a bromo compound. So the top one is the thionyl chloride. For example, here you have ethanol. If you treat it with thionyl chloride in the presence of pyridine, you would form ethyl chloride. That is also active now, can undergo different SN2 reaction. Here you have a cyclohexanol. In the presence of thionyl chloride and pyridine, you can convert the alcohol into the chloride. The mechanism for the thionyl chloride, for example, is you have OH. This is how you activate this in the presence of pyridine. So thionyl chloride is this compound. As I said, for the phosphorus, this center is relatively sigma positive and this sigma negative. That means that the OH can act electrophilically to the nucleophilic center like that. So that you would form now a very unstable activated compound. That means you have OSOCl, that is Cl minus, would be there. So you have HCl is produced, but you have pyridine. That pyridine would take out the acid. But here you have a bit. Here you have Cl minus that is floating on the reaction mixture. That Cl can come and attack that, and this can leave. So because you have converted it into a good leaving group, the chloride can attack as SN2 reaction. So basically that's how the mechanism of the reaction goes. So you have sulfur center that could be attacked, the chloride leaves, and once this is formed, the Cl minus acts as a nucleophile. Now, nucleophile would attack that carbon center. Similarly, the phosphorus tribromide also uses the same kind of mechanism. The OH coordinates to the phosphorus. One of the Br comes in attack in a substitution pattern. So if you just look at this, all of the OHs are converted into the corresponding bromo alkyl halide. So remember two reagents now. Alcohols can be substituted into alkyl chloride or alkyl bromide using thionyl chloride. We call it thionyl. This is called thionyl chloride. In the presence of pyridine, that would be, this is phosphorus tribromide. This is phosphorus tribromide. So remember these two reagents. Previously for dehydration, we have used phosphorus oxychloride. That's for dehydration, removing OH into alkene. But here, these two reagents are substitution. They yield substitution product of alkyl halide. Okay, we'll continue with one more very important, very versatile organic reaction. It's called tosylation. That means the OH is converted into tosylate. Tosylates are a very, very good leaving group. That's what we commonly use on organic synthesis. So these are all the reagents that has been used for converting it directly to alkyl halide, but the tosylation gives you a very good stable intermediates that can be attacked by any nucleophile of your choice to make a substitution product. So that is called a tosylation of alcohol. The tosylate is a very good leaving group. So that will continue in the next section. Moving on to other reactions or conversion of alcohols into a good leaving group so that you could do a good substitution reaction would be tosylation, meaning that the alcohol would be converted into a good leaving group, such as what you see here. This is a good leaving group. This is what you form. This reaction is called tosylation, meaning that first you convert the alcohol into a tosylate. A tosylate group is a very good group, good leaving group in a synthesis of changing alcohols into other substitution products. So once you made this, you could attack this carbon and this would leave, and then you can substitute with the alcohol. You know, the alcohol, the OH is not a good leaving group, but you can make it into a good leaving group by tosylation and then continue with your reaction. A tosyl group is this. This is actually derived from tosic acid. Remember, we have discussed this before for protonation of alcohols. That's a tosic acid, paratoluene, sulfuric acid. But there is also a tosyl chloride, which is this very active one to react with alcohol. Instead of just donating proton, this is tosyl chloride. Tosyl chloride is this. This is tosyl chloride. That's what you use to convert the alcohol into a tosylate, because this OH can heat this sulfur and the chlorine leaves, and in the presence of pyridine you can tosylate the alcohol. Once you tosylate it, the alcohol now becomes a good, has a good leaving group on it, which is a tosyl group, tosylate. Then you could react with different nucleophile and substitute it for whatever you need. For example, here you have ethanol, tosylation using a tosyl chloride, tosylation reaction. That means you tosylate with sulfonyl chloride in the presence of pyridine, you convert it into ethyl tosylate. So this is CH3, CH2. In short, we write it as OTS, tosyl or tosylates. So this is representing this whole thing. So if you have a nucleophile that can heat this carbon, then that can easily leave, and then you can substitute it with any nucleophile you want. So the intermediate tosylation is very important to make your alcohol into a good leaving group. That is a tosyl group. A tosylate group is a very good leaving group. That's what you need to remember. Here you have this alcohol with a very good stereo center, but you have this alcohol. You want to substitute this alcohol with some other nucleophile. First, you need to tosylate it. You can tosylate it using tosyl chloride and pyridine. Tosyl chloride is this, remember, and you would have that structure on it. So this is basically CH3 in short, when we write it in short. That's H, CH3, the same, O, T, S. So you don't have to write every time this large group. You can represent it as a tosylate group. So if you have a nucleophile now, a nucleophile can come and easily attack that carbon, and the tosylate leaves. So you are able to substitute the alcohol with the nucleophile through first tosylating it. Otherwise, you cannot just, any nucleophile hitting this carbon cannot replace OH. Is not a good leaving group. So your product looks like now CH3, a nucleophile comes in. So the nucleophile would be here, and CH3 would be here, and H can't be here. So that's what we see now in terms of, because there should be an inversion of configuration. That's why I just changed the stereochemistry there. It might, okay, it's coming in, so it generates this. Let's see, for example, here, what is the stereochemistry of this? This is priority 1. Priority, actually, since these are two CH3s, there is no stereochemistry. It's not very important to say this is not this is not a chiral center. What I mean is because you have two metal groups on the same carbon, so it doesn't matter where you put it. But anyways, the nucleophile hits this carbon and the tosylate lives like this. So you would produce this substitution product. You couldn't do this directly on OH. So if you are asked to synthesize some transformation of an alcohol, you should always remember that the alcohol cannot be just kicked out by a nucleophile. So what should come into your mind is, oh, okay, if I tosylate this alcohol, that would be a good leaving group. So with any nucleophile I have at hand, I can just substitute that alcohol or that tosylate. So this is very important reaction in organic synthesis, especially in undergraduates. You need always to remember, oh, tosylation or a tosylate group makes the alcohol a very good leaving group for substitution reaction. So I will give you some more examples in the problem solving session on tosylation and their reactions. Now we can review some reaction of tosylates as SN2 or E2 reaction. Here I have ethanol. You can convert it into tosylate by reacting it to tosyl chloride and pyridine, we have seen before. So you have a good leaving group now, tosylate. You have sodium ethoxide, which acts as a nucleophile. That's OCH2 CH2CH3. So this is a negative charge, plus is sodium. Sodium doesn't participate in the reaction, obviously, but the ethoxide would attack this carbon as SN2 reaction would replace to make this diethyl ether. Diethyl ether. So the purpose of the tosylate is you cannot just convert the OH, which is alcohol, directly to the ether. You have to convert it to something, a good leaving group for SN2 reaction. So tosylates are very versatile in the application of organic synthesis. Here you have the same ethanol tosylated. You form this tosylate through this tosyl chloride and pyridine reacted, and now you have a bulky base. This is a base which is potassium tertiary butoxide, bulky base. So it would act not as a nucleophile, rather it acts more as a base. If it acts as a base, the elimination reaction would produce this ethene, an alkene. So basically the transformation of an alcohol to an alkene. Here in this one, we have an S configuration alcohol. That's the stereochemistry around this chiral center. You want to convert it to a cyano compound through a nucleophilic substitution. To do that, first you have to convert this into a tosylate. The tosylate of this gives you this by reacting it with tosyl chloride and pyridine. So you are tosylating that. During tosylation, there is no change in the configuration because there is no bond that's broken on this compound. It is just rather having the tosylate reacting on this OH. So whatever was S still is S. But the next step, you have to be careful now. This is potassium cyanide. The cyanide is a nucleophile, good nucleophile. So that would attack this carbon, and the tosylate would leave. So it's a substitution SN2 reaction. Remember from our previous stereochemistry discussion, long time in the previous chapters, SN2 nucleophilic attack of substitution always results in the inversion of configuration. That means if you had an S, when the cyano group comes and attacks this carbon, when the tosylate leaves, whatever was S, now it is an R. So it's a confirmation that this is an inversion of configuration for an SN2 reaction. So that's the conversion. So the S alcohol cannot be directly converted to cyano compound unless you convert the alcohol into a good leaving group, a tosylate. So you can see the application of tosylates to do different reactions. Here also, at the end, it's a methoxy group is here through methoxide nucleophile. This is a nucleophile here, nucleophile. This is called methoxide. This is a cyanide. So the methoxide would attack this carbon and substitute it right there. But before you do the tosylate substitution, you have to convert this reaction. Tosylated, as I said, tosylation doesn't change the configuration of the carbon right here because there is no bond that's broken when you do the tosylation. Once you make a tosyl, the cyano group comes from the back and attacks this. Then you not cyano, sorry, the methoxide, CH3O, comes from backside and attacks the tosylate as a nucleophilic substitution. So this leaves. So that's an SN2 reaction. So the inversion of configuration happens because it comes from the back. So whatever was R, now we have S. That's inversion of configuration in SN2 reaction. So overall now we saw the application of tosylates on alcohols. Alcohols react with tosyl chloride and pyridine to form a very stable intermediate compound which is called tosylates. Those tosylates can undergo elimination, substitution, and so on through this kind of reactions. So this part of the discussion concludes the reaction of alcohols. Now in the next series we'll go to reaction of ethers and then the reaction of epoxides.